$1 billion is the estimated valuation shared by masterpieces like the Mona Lisa and Starry Night, yet both icons are built upon the exact same material foundation of professional oil paint. Why has this specific medium remained the primary choice for preserving artistic vision across 5 centuries of history? At first glance, the substance appears to be a simple colored paste, but in reality, its creation requires a sophisticated convergence of chemical engineering and geological extraction. The journey of a single tube involves deep earth minerals, intense thermal processing, and high-precision mechanical milling. Behind the label of every professional pigment lies a hidden world of laboratory testing that lasts for several months. Engineers monitor every individual pigment particle to ensure it meets strict micron-level specifications. One can notice how automated dispensers release a single drop of linseed oil, measured with such accuracy that deviations are non-existent. Why is such extreme precision necessary for a product intended for creative expression? To the naked eye, a minor change in the oil-to-pigment ratio might seem insignificant. But without this mathematical rigmarole, the resulting paint would lack the chemical stability required to prevent cracking or fading over hundreds of years. It is visible how the heavy steel rollers of a 3-roll mill rotate at varying speeds to shear the mixture into a perfectly smooth consistency. This process is only gaining momentum. After the initial blending, the paste undergoes thermal cycles to test its durability against environmental shifts. It only looks obvious that mixing color and oil creates paint, but in reality, the interaction at a molecular level determines the final refractive index and the light fastness of the artwork. The equipment gradually refines the texture until the grit is completely eliminated, ensuring that the light reflects evenly off the surface. Everything only gets more complicated as the technicians transition to the next level of quality control, using spectrometers to verify color constancy across different batches. The material eventually reaches a state of chemical equilibrium, ready to be sealed into airtight tubes. From here, the finished medium begins its transition from an industrial product to a tool for the next generation of masterpieces. 75% of the volume inside a single high-end tube of oil paint consists of pure, concentrated pigment. Why is such a staggering density of raw material necessary for the artist? It would seem that a lower concentration could still provide color, but in reality, this extreme saturation is the mechanical reason behind the deep tones, immense coverage, and vivid intensity that define the medium. The internal composition of the paint far exceeds that of acrylics or other modern synthetic alternatives, ensuring that the visual impact remains consistent over centuries of exposure. Oil paint serves as the most durable and long-lasting medium in the entire history of Western art. Works created several hundred years ago still retain their depth, emotional resonance, and chromatic integrity almost entirely intact. One can notice how the chemical bond between the oil and the mineral particles creates a structural shield against the passage of time. The equipment used to grind these materials must operate with extreme precision to ensure every grain is coated. But this is just the beginning. Certain pigments throughout history were literally valued more than gold due to the difficulty of their extraction. Ultramarine was traditionally derived from lapis lazuli stones mined exclusively in the remote regions of Afghanistan. The process of transporting and refining these minerals into a usable paste was an undertaking of immense physical labor and high financial risk. It only looks obvious that colors are readily available today, but in the past, they represented concentrated wealth and geography. 12,000 sea snails were required to produce just a few grams of the legendary Tyrian purple pigment. This biological extraction process was so grueling and resource-intensive that the color became a symbol of absolute power and status. The equipment of the era had to process thousands of organisms to yield a microscopic amount of dye. The process is only gaining momentum as chemical engineering eventually replaced these natural methods. One can notice the weight of history in every brushstroke, as the medium is not merely a liquid for decoration. It represents a complex fusion of geological minerals, sophisticated chemistry, and centuries of human effort. The transition from raw earth to a stable artistic medium involves a sequence of crushing, filtering, and mixing that has remained largely unchanged in its core logic. The material stands as a testament to historical value, where every tube contains the legacy of global trade and scientific discovery. From the depths of mines to the careful synthesis in modern laboratories, the evolution of paint continues to preserve the visual record of civilization. Thus, the steel-like permanence of the oil medium ensures that the creative intent remains visible for generations to come. 100% of the quality found in oil paint depends entirely on the initial stage of pigment preparation. Why is such meticulous attention paid to the raw material before a single drop of binder is added? The answer lies in the molecular stability of the final product, as any inconsistency in the source material will lead to the eventual degradation of the artwork. This foundation begins with the careful selection of raw pigment sources, which may originate from natural earth minerals, complex metal compounds, or synthetic variants engineered within specialized laboratories. But this is just the beginning. It only looks obvious that raw minerals can be transformed into color, but in reality, the source material is initially unusable. One can notice how the raw particles are uneven in size and saturated with various environmental impurities. High-power mechanical grinders first break down the primary structure of the material through a sequence of pre-grinding actions. The equipment gradually reduces these fragments before they are passed through industrial sieves to eliminate coarse grit and fine dust that fails to meet technical standards. Testing for purity and lightfastness follows this mechanical refinement. A pigment must demonstrate the ability to maintain a stable color profile for hundreds of years without fading under ultraviolet exposure. It gets more complex further on. All remaining moisture is extracted through a complete drying cycle to prevent unwanted chemical reactions or clumping when the powder eventually meets the carrier. The process is only gaining momentum as the production shifts toward the binding agent. While poppy seed oil, walnut oil, or safflower oil are viable alternatives, linseed oil is utilized most frequently due to its superior drying properties and high durability. The camera glides along the pressing station where flax seeds are crushed to extract the crude oil. Multiple filtration cycles then remove every trace of mechanical residue and organic impurity from the liquid. At first glance, the resulting oil seems finished, but in reality, it must undergo chemical refining to lower the concentration of free fatty acids. This specific step is taken to limit the yellowing effect that occurs as the paint ages over decades. The equipment may gently heat the oil to further calibrate its viscosity and enhance its natural drying rate. The refined linseed oil eventually reaches a state of total structural stability. The purified binding agent and the stabilized pigment are now fully prepared to enter the mixing phase of the production chain. 150 grams of pigment may be the starting weight for a single test batch, but industrial production begins with hundreds of kilograms. Why must every gram of pigment and oil be measured with laboratory precision before they ever meet? A single % of deviation in the formula for a specific hue would render the entire batch unusable for professional artists. First, the linseed oil and liquid additives are poured into the mixing tank to create a stable, viscous wet base. Then, the powdered pigment is introduced into the oil at a measured, slow pace. This specific sequence allows the powder to absorb the liquid more evenly, effectively reducing clumping and minimizing the volume of pigment dust escaping into the surrounding air. One can notice how the dry powder gradually vanishes into the golden liquid. But this is just the beginning. Why is this initial mixture referred to only as a rough paste rather than finished paint? The process at this stage is not designed to create a smooth medium, but rather to ensure each individual pigment particle begins to be coated in a microscopic layer of oil. It is a physical reality that every pigment requires a unique ratio of oil to reach its ideal state. Fine particles with expansive surface areas demand a higher volume of linseed oil for saturation. Conversely, heavier pigments with coarser structures require significantly less. This physical variation explains why no universal mixing formula exists for all colors across the spectrum. At first glance, the process seems uniform, but in reality, it is the reason why every tube of oil paint possesses a distinct thickness, texture, and physical feel under the brush. Low-speed mixers are utilized during this phase, typically rotating at a rate of only 20 to 60 revolutions per minute. This controlled speed prevents the blades from pulling excessive air into the thick mixture, which would compromise its stability. Each individual batch requires between 15 and 40 minutes of constant agitation just to reach the status of a rough paste. If the initial color appears off-center, small amounts of pigment are added and reweighed with extreme care. The process is only gaining momentum. Any adjustments made now are strictly preliminary, as the final color depth can only be accurately confirmed after the mixture undergoes the grinding phase. One can notice the heavy rhythmic movement of the mixing blades as they churn the dense material. Safety protocols are paramount during this stage of preparation. Workers must wear comprehensive protective equipment because pigment in its powdered form is incredibly fine and becomes airborne with the slightest movement. To prevent inhalation of these microscopic particles, they utilize dust-filtering masks or specialized light respirators. Their hands are shielded by rubber or nitrile gloves to prevent direct skin contact with the linseed oil and pigments. Certain chemical substances used for coloration can cause significant skin irritation if exposure is prolonged over time. After the rough paste achieves the correct consistency, it is transferred to the grinding stage. The grinding process is the critical juncture that determines the fineness, color depth, and ultimate quality of the professional paint. In this industrial environment, a 3-roll mill is employed, featuring 3 large cylinders made of hardened metal, ceramic, or granite. These rollers rotate in opposing directions at different speeds, with the gaps between them set to tolerances as thin as a few microns. When the rough paste is pulled into the high-pressure zone between the rollers, immense mechanical force shatters any remaining pigment clusters. This forces every individual color particle to disperse deeply and permanently into the linseed oil. On the surface of the final roller, the paint is spread into an incredibly thin, shimmering layer. It is visible how the internal structure of the material shifts from a gritty mixture into a continuous, stable fluid. Everything only gets more complicated as the color begins to mature. The distance between the rollers is never static. It is recalibrated for every specific type of pigment in the production line. Harder pigments require the application of intense pressure, while softer or heat-sensitive varieties need wider gaps to prevent the destruction of their delicate chemical structures. Because of these variables, the grinding process requires the constant, vigilant supervision of skilled technicians and cannot be left to full automation. A single batch must pass through the mill between 2 and 5 times to reach a state of perfect dispersion. After each pass, workers use broad metal scrapers to collect the paint from the rollers. One can notice how they check the gloss and the way the paint pulls into long, elegant strings to assess its current quality. If the texture remains gritty or the color appears cloudy, the batch is immediately sent back through the rollers. Once the paint is finally stabilized in a holding container, it enters the rigorous quality control phase. This stage dictates whether the batch proceeds to the filling line or returns for further processing. The first check involves measuring the fineness of the pigment particles using a specialized gauge or a glass test plate. Even a microscopic quantity of particles larger than the established standard will cause the entire batch to be rejected and reground. Next, the viscosity is measured to determine how the paint will flow from an artist's brush. If the fluid is too thick, a calculated amount of oil is added. If too thin, the formula is adjusted in the opposite direction. Transition to the next level. While the paint quality is finalized, aluminum tubes are manufactured on a parallel production line. Aluminum is the material of choice because it is lightweight, durable, and highly resistant to corrosion. Most importantly, it serves as an absolute barrier against air, which is vital since oil paint dries through the process of oxidation. Thin sheets of aluminum are formed into hollow cylinders, and the threaded necks are shaped to receive an airtight cap. Inside, a protective coating is applied to prevent any chemical reaction between the metal and the linseed oil during years of storage. The equipment gradually washes and dries these tubes before they undergo airtightness testing. A single defect in a seam would cause the paint to harden prematurely. When the tubes pass inspection, they move to the filling area. This is where the viscous paint is transferred from storage containers into its final commercial housing. Because the material is highly sensitive to air, the filling process is executed with steady, controlled movements. The tubes are secured in holders on a conveyor, while a piston system or low-pressure pump injects the paint. This method ensures the flow remains steady without creating turbulence that could trap air bubbles. Each tube is precisely weighed to ensure the volume is consistent with the manufacturer's specifications. Due to the high viscosity of the paint, the pumping speed is intentionally limited to prevent air pockets that would reduce the product's shelf life. In semi-automatic lines, the output ranges from 20 to 60 tubes per minute, while fully automated systems can reach speeds of 200 tubes. After filling, the tubes move to the crimping stage where the open bottom is sealed. A specialized machine folds the aluminum edge 2 or 3 times to create a permanent, airtight seal. Before this fold is finalized, some systems perform a light compression to evacuate any remaining air from the interior. One can notice the machine stamping the batch code and production date directly onto the flattened fold for future traceability. Finally, the cap is tightened onto the neck, completing the structural integrity of the container. The process is only gaining momentum as the sealed tubes move toward final packaging. Each unit undergoes a visual inspection for mechanical flaws, such as dents or leaks in the crimped seal. The tubes are then placed into individual boxes or specialized trays. These packages are printed with essential data, including the color name, code, series number, and safety information. Automated machines can pack hundreds of units per minute before they are grouped into large cardboard cartons for global shipping. From this point, the oil paint is ready to enter the distribution chain, traveling to art supply stores and the studios of artists around the world. Thus, the material reaches the standard ready for the final stage of its journey. 100% of the chemical properties found in traditional professional oil paints are preserved in a specialized alternative known as oil sticks or oil bars. Why would an artist choose a solid stick over a classic tube of paste-like pigment? It might seem like a completely different medium at first glance, but in reality, these are genuine oil paints where only the physical form and the specific ratio of internal ingredients have been modified for a different tactile experience. The formula is carefully adjusted to transform the substance from a soft paste that requires squeezing into a thick, solid, and firm material capable of being held directly in the hand, like a drawing implement. But this is just the beginning. To reach this structural integrity, a small but precise amount of natural wax, typically harvested from bees or derived from specific plant bases, is integrated alongside the concentrated pigment and linseed oil. This wax serves as the critical binding agent that allows the paint to maintain its distinct cylindrical shape. One can notice how the stick remains firm to the touch, yet stays sufficiently soft to glide with oily smoothness across the fibers of a canvas. The manufacturing process for these sticks follows the exact sequence used for traditional tube paints until the final stages. It only gets more complex further on. During the formula adjustment phase that follows the initial grinding of pigments, the natural wax is introduced and subjected to thorough mechanical mixing to establish a consistent semi-solid architecture. The equipment gradually pours this heated, homogeneous mixture into specialized cylindrical molds to set. One can notice how the material cools and solidifies before being precision cut into individual units. The process is only gaining momentum as each stick is finally encased in protective paper or plastic sleeves to prevent premature drying or damage during transport. Oil sticks provide the unique ability to apply color directly to a surface without the mediation of brushes or palette knives. This creates a physical working experience that closely mirrors the use of pastels. At first glance, it looks like a simple drawing tool, but in reality, it fully retains the professional characteristics of oil media, including the ability for complex layering, seamless blending, and the assurance of long-lasting color durability over decades. The solid paint remains workable on the surface, allowing for the same technical depth as its fluid counterparts. From here, the transformation of the artist's toolkit moves toward a fusion of drawing and painting in a single gesture. Thus, the production of these specialized bars concludes, providing a versatile alternative for the modern studio. 100% precision is the baseline requirement for every individual stage of the industrial journey that transforms a mixture of oil and pigment into professional oil paint. Why is such a rigorous level of technical accuracy necessary for a product that appears so simple? It only looks obvious that mixing these two components would yield a usable result, but in reality, the slightest deviation in the selection or preparation of raw pigments would compromise the chemical stability of the final medium. The process is only gaining momentum once the base materials are verified against strict manufacturing benchmarks. Refining the linseed oil serves as a critical preliminary phase. One can notice how the equipment gradually purifies the oil to ensure it possesses the correct viscosity and drying properties. It gets more complex further on. Engineers introduce the prepared pigments into the refined oil, initiating a mixing process that occurs at strictly controlled low speeds. This slow rotation prevents the introduction of excessive air bubbles and ensures that every grain of pigment is thoroughly coated with the oil medium. At first glance, this mixing appears to be the final step, but in reality, the mixture is still far from the smooth consistency required for artistic use. The camera glides along the heavy machinery as the dense paste moves toward the most delicate part of the production line. Grinding the mixture through a series of steel rollers requires a level of mechanical calibration that is measured in a few micrometers. These rollers rotate at different speeds to create a shear force that breaks down any remaining pigment clusters into a perfectly uniform dispersion. It is visible how the paint forms an even layer as it passes through these microscopic gaps, achieving a texture that no manual process could replicate. Everything only gets more complicated as the batch enters the quality control phase. Automated systems and technicians verify the color density, light fastness, and drying time of the dispersion. Therefore, every batch undergoes a final assessment before moving to the high-speed filling lines where empty tubes are positioned for the injection of the paint. The equipment gradually fills each container with a specific volume, ensuring no air remains trapped inside before the metal is crimped shut. This mechanical seal must be airtight to prevent oxidation during storage and transport. One can notice how the final tubes are placed into their packaging, marked with technical data and batch numbers. The material leaves the assembly line, transitioning into a calm stage as it is prepared for distribution to studios and galleries worldwide. Thus, the production cycle concludes, having transformed raw minerals and oil into a refined tool for creative expression.